Hey everyone, this is the Bridge for Math coming at you again with another video. Totally hot. This one's called PFD, not BFD. Hey, come on, get your mind out of the gutter. PFD is partial fraction decomposition. So I want to talk to you about the idea behind partial fraction decomposition. Let's look at each word. Fraction, you know what a fraction looks like, 1/2. Decomposition, when you think of decomposition in biology, it means things breaking down, breaking things into different smaller components. Don't worry about the idea of partial, that's not needed right now. But this concept is basically taking a complicated fraction and breaking it into two smaller, simpler fractions. So I'd like to say that you've done this reverse in the past. So let's look at what you did before. Before, you'd start with two fractions, simple fractions, and you'd make it into another fraction. So let's look at 1/2 plus 1/3. I want to remind you, when you're adding or subtracting fractions, your whole goal is to get that common denominator. I tell people just to look at the other side. 2 goes, oh wow, there's a 3 over there. So you're going to multiply by 3 over 3. You're essentially multiplying by 1. Do you remember that? So 1/2 times 3 over 3, or 1/2 times 1, is still equivalent to 1/2. But 1/2 times 3 over 3 is 3/6. Remember with fractions, multiply numerator times numerator, denominator times denominator. So I'm doing a lot of review, but that's okay. Same with the 1/3, you go, oh, the 3 goes, wow, look at the 2 over there. So you multiply by 2 over 2. You come up with, look at how I kind of wrote this improper fraction. You see how you got your common denominator is 6, you have 3 plus 2 over 6. I left that as the complicated version, and obviously you know 3 plus 2 gives you 5, 6. But let's go ahead and take it up a notch and go to adding polynomial fractions. So 6 over x plus 1 minus 2 over x minus 3. Two fractions, kind of uglier because they're polynomials. But notice this is linear and that's linear. That means to the power of 1, right? So how do we subtract fractions? Well, we need to get a common denominator. Let's follow what I did here on the early, easier example. Look at the x plus 1 and go, oh, wow, I wish I had an x minus 3. So you multiply x minus 3 over x minus 3, which is, what is it? 1. 6 over x plus 1 times 1 is the equivalent, right? But now you're getting the common denominator of x plus 1 and x minus 3. Likewise, with this piece, 2 over x minus 3 is going, whoa, x plus 1. So, multiply x plus 1 over x plus 1. Again, you see this concept of multiplying by 1? Totally helps you out. Now we're getting a common denominator. Remember I said numerator times numerator? What's 6 times x? 6x. What's 6 times negative 3? Negative 18. So all you're doing is distributing or multiplying through, correct? So notice we got a common denominator. When you have two fractions with a common denominator, all you have to do is add or subtract the tops, the numerators. So in this case I have 6x minus 18. Now here's a trick thing that I didn't put the parentheses like I normally do. What do you think this minus right here does? It distributes across everything in the numerator. So this would be minus 2x. So let's look at this. What's 6x minus 2x? 4x. What's negative 18 minus positive 2? Negative 18 minus the plus. So this is where people make the mistake, so pay attention. This minus sign distributes across every piece over here. So that minus goes to the positive 2, which makes it minus 2. What's negative 18 minus 2? Negative 20. So do you agree we started with simpler fractions and made it more complicated? Now I know some of you are out there going, well, don't you multiply these things? The answer is yes, you could if you wanted to kind of go further and simplify, and you'd get x plus 1 times x minus 3, you'd get a quadratic of x squared minus 2x minus 3. But I'm going to tell you with partial fraction decomposition, it's nicer when you have these different multiplication pieces, these factors. So notice again, two simple fractions, you actually made it more complex, but that's called taking two fractions and making it into one. Well, that's the past. What we're doing now, partial fraction decomposition, which you will see in calculus when you're doing some intense integration, but that's another class. So this comes back at you, but I like to look at this. If you want to know something, do you agree when you know something really well, you know it frontwards to backwards, backwards to front, like A, B, C, D, E, F, Z, Y, X, you know it both ways. So we're going to make you a fraction ninja, which is kind of nice. You never know when you might have to fight a fraction. Check it out. So here we go, partial fraction decomposition, And the form we're going to learn is when you have distinct linear factors. And I do have to confess, there are other forms of partial fraction decomposition, but they're basically the same formula, same process. I'm just showing you the one where you have distinct linear factors. So let's talk about what the heck that means. Do you remember this that was on the board before? This is the complicated fraction. Do you see these distinct linear factors? Y equals mx plus b, x plus 1 is a linear factor. X plus 1 is a linear factor right there. X minus 3 is a linear factor. So I'm taking this complicated fraction and I'm going to try to break it into, depending on the number of linear factors, there's 2 here, so I'm going to have a plus b. So had I had a third factor, I would have had plus c over that factor. But in this case, we have 2 factors, so I literally have 2 unknowns, a and b. Well, now you have an equation and you're like, oh my gosh, there's so many fractions, I want to go crazy. No, let's handle the heat. Let's make you really excellent fractions. How do you really destroy fraction equations? You multiply both sides by the common denominator. In this case, the common denominator across is x plus 1, x minus 3. So notice, I'm multiplying, I changed it to sexy red, x plus 1, x minus 3, multiplied it by the left side, and I'm taking x plus 1, x minus 3, and I'm multiplying it by the right side of the equation. Well, what happens when you have something multiplied and something on the bottom that are the same? They cancel out. So this ends up with 4x minus 20, which is what you're going to see over here. This side's a little bit more complicated, and I want to show it to you. What cancels out with this first term? Do you agree you multiply everything inside the parentheses or brackets? Yes. So the x plus 1s will cancel out, but this x minus 3 is still left over for the a. And that's what you have, a times x minus 3. Then you multiply this entire thing by the second piece, b over x minus 3. Well, do the x minus 3s cancel out this time? Yes. What's left over? X plus 1 times b. I showed the work a little bit separately there. People make the mistake by not multiplying both pieces by everything. But you won't, because you're watching this closely and you're hitting the rewind on the video. So literally we have one equation set up with these 2 unknowns. And you might go, oh, 1 equation, 2 unknowns, you're in trouble. But what I want to share with you is there's 2 pieces of information. So let's watch this through. Multiply everything out. So a times x minus 3 is ax minus 3a. Multiply b times x plus 1, bx plus b. I hope you see where we multiplied that out. Now, what I want to encourage you to do, get all the x terms together. Do you agree you can bring the like terms together? So you have ax plus bx, those are the x terms. But what about just the regular numbers without the x's? You have negative 3a plus b. Notice I put parentheses around them, just kind of highlight they're different. Well, I want to factor out a, or factor out the x, the greatest common factor. So you have a plus b times x. Here you just have the number. But now I want you to look at this. Do you agree you have a left side equals a right side? So how many x's are on the left side? You have 4 x's on the left side. Well, if you have 4 x's on the left side and there's an equal sign here, how many x's need to be on the right side? Yeah, 4. So literally 4 is going to equal a plus b. Notice how I put the 3 underlines here to say that has to be equivalent. So 4 is equal to a plus b. And that's where I got this first equation. We're going to end up getting a system of equations that we're going to solve. And then what about the negative 20? You have negative 20 on the left side. You know a number by itself. What's on the right side? Negative 3a plus b. So that has to equal negative 20. Notice I have this little squiggly line to represent they have to be equal. So now I have negative 3a plus b equals negative 20. Now you have 2 equations, 2 unknowns, and you're in the driver's seat ready to crush it. So again, you can do elimination method, additive method, whatever you want to do. I just said the b's look like we could easily cancel them out by multiplying the first equation by negative 1. So negative 1 times that first equation gives you negative a minus b equals negative 4. You add it to equation 2, so this is elimination of equations. You end up getting negative 4a equals negative 24. You get a equals 6. Easy to find out what b is. If a is 6, what do you think b is going to be? It's going to be negative 2. Now watch this. Let's go back to the board. Oh my gosh, there's the 6, which was over x plus 1, so a is 6 like you found. Plus b, well we found b was negative 2, and look at this minus 2. So you might have to look at that a few times. This is partial fraction decomposition with the bridge for math. I hope that helps. Keep coming back to the Bridge for Math. Rock out, okay, everyone? Take care.